Tá ao vivo agora.
Só descontar, viu? Você não sabe se aquilo é. Você não sabe se pode ficar.
Esse aqui, ó. Tá bom.
É aquele computador ali. Com água, negócio, eu parei.
A palestra oficial.
É tipo uma série normal, só que cada nota guarda um nível todo legal. Traz por baixo. Vai perder um pouco de lousa, mas. Só o Marcos não usar as pontas.
Dá certo aí? Olha bem.
Marcos, vai a extrema direita lá que tem um pedacinho do inferno.
Mas você pode fazer isso aqui, ó.
Is it working for? Aí tá bom.
Meu Deus do céu.
Isso é muito bom.
Só não tosse no microfone. Fala uma palavra, cara.
Fala teste 1, 2, 1, 2, 2. Aumenta o volume. Mais ou menos aqui.
Agora tá bom.
Hi everyone. Now we begin our second week of our winter camp. The instructor for this second week is Marcos Cahuacan. Most of you know him. Maybe you have already seen him last week competing with you, but different names. Most of the time he plays second just like himself. So that's how he is. Well, Marcos, it's your time. All right.
Well, good morning, everyone. I hope you had a good weekend. So, I was struggling a bit to decide on a topic to talk on this first day, and I eventually came across a very interesting data structure that solves a really cool problem that I'm going to show you guys. The cool thing about the structure is that it's relatively easy to implement. The algorithm itself is not so complicated. The problem is that proving its correctness is a pain in the ass. It's really hard. And, well, hopefully I'll be able to convince you guys that the algorithm is correct. And I'll probably spend the whole lecture talking about it. Alright, so let me first present the problem that is the motivation behind this structure. I'm gonna draw that. Suppose you have a directed graph. I have something. This is copy the example. So suppose we have this directed graph, and what I want to know is, for every vertex besides this special vertex, which I'm going to call the source vertex, I want to know, for instance, for vertex D, whether there is a vertex that appears on every path from S to D. So for instance, every path from S to D has to go through B, right? There's no other way to reach D from S without going through B. Are there any other vertex? No. Let's take our example, vertex E. No, this is bad. Let's take A is bad. If you look at every path from S to A, you'll notice that every path has to pass through B and C, right? So the problem is really simple. For every vertex, I want to know what are all the other vertices that appear on every single path from the source vertex to this vertex. Is that clear? Okay. Let me name these guys. So, Bethany. Reggie. So the name of these guys is dominators. So when a vertex appears on every single path from the source vertex to another vertex, we say that this vertex dominates the other one. Okay? So in that example, S pretty much dominates everyone. By convention, we say that the source vertex dominates every other vertex. C dominates A, E dominates E, and so on. Okay. Cool. Let me define one more thing. Okay, so what is an immediate dominator? An immediate dominator is a dominator of W, but it has a special property. Every other dominator of W also dominates V. Alright, so let's see. Let's find immediate dominators in this graph. Immediate dominators. Well, as the source vertex, so S has no dominators, so as a consequence, S has no immediate dominators. What about A? Does A have any immediate dominators? C, right? What are the dominators of A? It's S, B, and C, right? But S and B also dominate C. So C satisfies the property of immediate dominator. What about B? Well, the only dominator of B is S, right? So S by itself satisfies the immediate dominator property because there are no other dominators. What about C? What are the immediate dominators of C? Yes, B, right? The dominators of C are S and B. Yeah, S dominates B, so B is the immediate dominator of C. What about B? B. Yeah, once again, the only dominators of D are S and B, and S dominates B. So B is the immediate dominator. And lastly, E. Are there any immediate dominators of E? Here are a lot of different letters. It's B. What are the dominators of E? It's just S and B, right? And S dominates B. So looking at this, you might start guessing that every vertex has at least one immediate dominator, which is true. I'm going to prove that. But more than that, every vertex besides the source vertex has exactly one immediate dominator. And that's a bit harder to prove. I'm going to prove both the statements. What's so funny? Okay, when I write one here, it's because you know there are many more to come. Okay, so I'm gonna prove existence first, and then I prove uniqueness. Uniqueness is actually pretty easy. All right. I'm not gonna write the formal proof, just gonna draw. Consider any path from S to B. We know that since B is not a source vertex, it has at least one dominator, right? Because the source vertex dominates every other vertex. Cool. So let's highlight every dominator that appears on the path from S to B. That might be dominator here, here. But the same dominator might appear more than once because the path doesn't necessarily have to be simple. But suppose that these are all the dominators. So, cool. We know that every dominator has to appear on the path from S to B. That's the definition of dominator. Now, consider the last dominator that appears on this path. Call it U. Now I claim that U is an immediate dominator of V. So, why is this the case? Suppose that U is not the immediate dominator. Right? Then this means that there exists some other dominator of V, let's say U, that does not dominate U, right? That's the definition of immediate dominator. So, W. Okay. Well, what does this mean? Since W does not dominate U, this means that there exists a path from S to U that does not contain W, right? Otherwise, W would dominate U. So consider such path. Colors. Let's say. Right. We know that this path does not contain W. Now consider this path that is formed by this pink path and this final path of the original path. Okay. We know that there are no other dominators from after U because U is the last dominator. So this means that this path that I just built does not contain W. This is a contradiction because W is a dominator of V. Every path from S to V has to contain W. Right? Cool. So we reached a contradiction. So this means that this guy cannot exist. So every other dominator from V has to dominate U. Hence, U is an immediate dominator. Is that clear? Cool. So this proves existence. And uniqueness is fairly easy. Suppose that a vertex has two different immediate dominators. So U and V, and they both immediately dominate W. And now consider any path from S to W once again. S. One of them has to appear first, right? Suppose U is the first one to appear. So we know that in this segment of the path, V does not appear. So we found a path from S to U that does not contain V, which means V does not dominate U. This is a contradiction. Right? Oh. First theorem out of 5 is done. Where are my notes? Okay. I'm gonna use one. Since we know that the immediate dominator existence is unique, I'm gonna use some notation here. I dominator I dom. All right. Cool. Okay, we know that every vertex has an immediate dominator. So consider now the graph formed by the same set of vertices, but the edges now will be formed by the immediate dominator and its dominated E. And I better write. Okay, so if you take all the vertices and their immediate dominators and connect each other, we will get a tree, and we call this tree dominator tree. Okay. It's not immediate that this graph is connected, but the thing is that if you start from any vertex and keep going to its immediate dominators, so I dom. Eventually, you will reach the source vertex, right? Because the source vertex dominates every other vertex. Is that clear? Or do you want me to explain?
You define that, right? You have to, you need to have a source vertex that dominates it.
Yeah. What do you mean?
There are graphs
Okay.
such that there's no vertex.
Yeah, if that's disregard every vertex that is not reachable from S from now on.
Okay.
You could say that S dominates this unreachable vertex because there are no paths from S to this vertex. But in general, these are like corner cases and such. We're not very interested in those cases. Okay. But yeah, that's a good point. Yes. So for now, I'll suppose that S reaches every other vertex. Okay. So yeah, if you start from any vertex and keep going, the immediate dominator eventually will reach the source vertex. So this means that every vertex can reach the immediate of the source vertex, so the graph has to be connected. Okay. And we call this tree the dominator tree. And this dominator tree has a really cool property, which is stated by theorem number 2. So the dominator tree is rooted at the source vertex. Right? So with that, we have ancestors and descendants defined for every vertex. our tree will look something like this. So suppose this is the dominator tree for some graph. Well, this theorem is saying that for any vertex V, the dominators of V are all the ancestors of V. In this case, just this vertex. For this one, these two are dominators of the V. And that's if and only if. So, if vertex X is the descendant of vertex V, then we know that V has to dominate X. And this is pretty cool because if we have the dominator tree of a certain graph, then we can check basically in constant time whether one vertex dominates another one. Because checking descendancy in a graph like this can be done in constant time with some recomputation. You guys know how to do this. You calculate you run a DFS this graph, you store the pre-order and the post-order of each vertex, and then for vertex B, you have this cool property that every node in the symmetry of V will have the pre-order index greater than pre-order of V, and the post-order index less than the post-order of V. And that's if and only if, so you can check this if a vertex belongs to the symmetry of V constant time. So yeah, dominator trees are pretty cool. Finding them are very difficult. Okay, let's prove this theorem first. The converse is trivial. So the converse is if V is a proper intersection of W, then V dominates W. So in this case, we have to prove that V dominates W. But V is the immediate dominator of this guy, right? And by definition, immediate dominator also dominates. So V dominates this guy, and this guy dominates this guy, right? For the same reason. And dominance is a transitive relation. If A dominates B and B dominates C, then A must dominate C, right? Because every path from S to C has to pass through B, and every path from S to B has to pass through A. So every path from S to C has to go through A. Okay. So yeah, converse is pretty easy. So now, suppose that V dominates the V, and we have to prove that V is an ancestor of the V. Okay. Suppose that's not the case. So, have some vertex V, and W is in a different subgroup. And we know that V dominates W. But why this cannot happen? Well, V dominates W, right? And this guy is the immediate dominator of this guy. By the definition of immediate dominator, if V dominates W, then V must dominate this guy as well, right? Okay, but this guy is the immediate dominator. Immediate dominator. But for the same reason, if V dominates this guy and this guy is the immediate dominator of this guy, then V must dominate this guy, right? By the definition of immediate dominator. So in the end, we can keep going up in this tree. And by inductive argument, you will see that this guy must dominate every single vertex on the path from the root to W. But that's a contradiction because in the end, you will know that V dominates the root vertex, which is the source vertex. And that cannot happen because no vertex dominates the source vertex. Cool. Okay. Okay. Now that we know what a dominator tree is, let's see if we can find any algorithm that finds a dominator tree. Let's not care much about complexity right now. So, naive approach. What would be one silly algorithm to find the dominator tree of a graph? The first thing you could do is, well, find the dominators of each vertex. How do you do that? So, if I have a vertex on this graph, and I want to know which vertices this guy dominates, I can just remove this guy from the graph and run the DFS from the source vertex and check which vertices became unreachable from us. These guys that became unreachable are the guys that are dominated by V. So in this time, you can run a DFS for every single vertex. You remove a vertex from the graph and see which vertices become disconnected, and then you will find for each vertex which vertices it dominates. Right. And with this information, how do you find the dominator? Well, consider a vertex V. With this bunch of DFSs, you will know which vertices dominates V, right? This guy. But we know that the immediate dominator is dominated by everybody else. So what we can just do is basically look at each guy, at each dominator of V, and check which one dominates the least amount of vertices. That guy is the only candidate for the immediate dominator, right? That view. So the first step of the algorithm runs in E times V time. That's V minus 1 DFSs. And the second part runs in V squared. You can check in linear time for each vertex which dominator is the immediate dominator. Okay. But we want to do better. E times V is too slow. And well, in order to do better than that, I need some extra tools. By tools, I mean more theorems, lemmas, and definitions, and notation, and so on. Okay. The first thing I need to do is define some numbers for each vertex, and these numbers will be the pre-order index of any DFS performed from the root, from the source vertex. First thing we're going to do is run a DFS. We're going to call 3. So we run a DFS starting from S. We keep track of the pre-order index for each vertex, and we're gonna call the DFS 3 by T. Okay. And now I'm going to do some notation because we're gonna use this stuff a lot, and this will help very much. Some more notation. I'm gonna denote by U arrow with a point over it V. If U is an ancestor of V in T. Okay. Yeah. Keep in mind that now I'm talking about the DFS tree, not the dominator tree. Okay. When I was studying this, I got confused and things was not making much sense. For now on, I'm gonna just talk about the DFS tree. Okay. Forget about the dominator tree for now. There's a plus sign over the arrow. We will say that U proper ancestor. The difference between an ancestor and a proper ancestor is that one vertex V is an ancestor of V. One vertex is an ancestor of itself, but it's not a proper ancestor. A proper ancestor is an ancestor that is not itself. That's the only difference. Gotta use that first. That doesn't work. Is it cool if I erase this part?
Yeah.
Let's introduce one more definition. This guy's gonna be really important to us. this is a confusing definition. So what is a semi-dominator of a vertex? It's a vertex with the lowest pre-order index, such that there is a path from this guy to W, such that the intermediate vertices have all pre-order index greater than the pre-order of the. Okay.
The path is in the original graph.
Good question. Yes, it's in G. Okay, let's make one big drawing to make things a little bit more clear. That should be it. Okay, so the edges and white are the three edges of the DFS, and the remainder of the edges are the other edges of the graph, of the original graph. Okay. Cool. Let's number this guy. 0, 1, 2, 3, 4, 5, 6. These are the pre-ordered indices for each vertex. Okay. Cool. Let's find semi-dominators. Yeah, one thing I didn't mention is that the semi-dominator always exists, right? Because the parent of a node is one possible candidate for semi-dominator. Because there are no intermediate vertices from this guy to this guy, so this condition is satisfied. But there is at least one vertex that satisfies this condition, which is the current vertex. So semi-dominator always exists. The problem is finding it. Semi-dominators. Okay, interactive part of the class. Well, S has no dominators, no semi-dominators. S is 40. Let's start with C. Who is the semi-dominator of C? S. Yeah, that's pretty easy, right? Because S has the lowest pre-order index of the whole graph. F. Who is the semi-dominator of S?
S again.
What?
It's the lowest pre-order index,
Yes.
so it should be S again.
Yes. There is this path. Wait, hang on.
C, right?
Is there a path from S from S to F that only goes through vertices with higher pre-order index.
Should be C, right?
What path?
Oh, okay.
It's higher than W.
And it must be higher than 2. It cannot go through C, for instance.
There's not.
There's not. I think there's not.
I don't think there's a path from S to F that only passes through vertices with
Yeah, it
higher.
is C.
It's C, right? Parent node. Now things start getting a little bit trickier. Who is the semi-dominator nearby?
S.
What is the path?
S, A, D, L, H, K,
Yeah,
and
perfect. If you look only at this subtree, you might think that the semi-dominator is kind of C because of this path. But actually, there's a path from S to I that only goes through vertices with high prior index, which is the path that Peter just said. S, A, Z, L, H, K, I. So yeah. Nice one. Okay. Same story, right? The same path works. Size. G. I think for G is C. J.
G.
Yeah, should be G. B is easy because fast is parent. S. Can go S, A, D, L, H, and then E. A is also S, same path works. You're getting there. A is easy. D is also easy. Is it? Yeah, I think it's B. And L. Yeah, it has to be B. Let me check the other one right now. I should have heard it. C says C, R says K says S, 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 S. Well done, class. You got them all right. Yay. Cool. Now that you guys understood what semi-dominators are, let's start proving a bunch of lemmas. Everybody likes lemmas. Okay, I lied. I'm not going to prove this lemma. The paper that I was using to prepare for this lecture simply skipped the demonstration of this lemma. I might give an intuition of why this is true, but I cannot give a formal proof. So basically what we have here is, you have two vertices and one has a lower prior index than the other. And you want to find a path from the first one to the second one. And this lemma states that every search path has to go through a common ancestor of V and W in the DFS tree. Well, the case where V is an ancestor of W is trivial, because V is such path. So, suppose that's not the case. And I don't know, consider the LCA of V and W, the lowest common ancestor. Now, due to the nature of the DFS search, there cannot be any edge going from this subtree to this subtree. Okay? Because cross edges can only connect, can only take one vertex to a vertex low with higher, lower prior index. So this cannot happen. So the only thing you can do from V is either go up in the tree, following back edges, or going more to the left, so there's subtrees here. These are cross edges, but this doesn't prove, right? You're actually getting worse, you're getting further from W. And actually the problem stays the same. This guy is a common ancestor, and there's no way to go from this guy to this tree anymore. So yeah, the only way you can reach W from V is by going through some back edges, reach some common ancestor, and then go down using forward edges or true edges. Is this enough to convince everyone that the lemma is true? I'm sorry, I cannot give a more formal proof. All right. Number 2. Right, EW is not a vertex. I now is the proper ancestor of the NT. This is pretty straightforward, right? Because the DFS tree only contains edges from G. So if you consider the path from S to W, since the IDOM is the dominator of W, then IDOM has to appear somewhere in this path. So the IDOM of W has to be an ancestor of W. Okay? That comes from the definition of dominator. Alright? Cool. Number 3. One similar. But this one states that the semi-dominator is a proper ancestor of the DFS tree.
People on the stream are saying that they can't read what's on the. So if you can.
Is it because it's too small or
Yeah,
because?
I believe so.
Okay. For now, I'll see if I'll write a little bit here. Yeah. Okay. So, why is this true? Suppose that the semi-dominator of W is not a proper ancestor of W. Okay. We know that the semi-dominator of the pre-order index of this guy has to be less than the pre-order of this guy, because the parent of W is a candidate for semi-dominator, right? And the semi-dominator is the one with the lowest pre-order index. So you know this. Preorder of this guy is less than the preorder. So now we invoke the lemma number 1, which I did not prove. To show that in the path from this guy to this guy, there must exist a vertex as a common ancestor of both the semi-dominator and the vertex. Okay? Gas dom is here. W is here. There must be a path from this guy to this guy. That goes to the common ancestor. But the common ancestor of these two vertices has to have a lower preorder index than those two, right? Because in the DFS tree, you reach this guy first before these two guys. So the preorder of this guy is lower than the preorder of these two. Yeah, so. I'm used to it. We have to consider a specific path here. Let me just explain this. Since this guy is the semi-dominator of this guy, then there is a path from this guy to this guy. That only passes through vertices that has preorder greater than the preorder of the, right, from the definition of semi-dominator. Okay, now it's going to work. So all these guys have preorder greater than preorder of the. And this guy is a common ancestor with these two. So this guy has a preorder which is less than or equal to the preorder of this guy. Right? Due to lemma 1. There is a common ancestor of this guy, of the semi-dominator and W in the GFS tree, which has to go through. And the ancestor has to have a lower preorder index from these two because the GFS tree reaches this guy first. Okay, so if we join these two things, we find that this vertex has a preorder index that is less than or equal to the preorder of this guy, but also satisfies the condition for a semi-dominator for this guy. Because this path only contains vertices that have preorder greater than the preorder of the. Okay. So we would actually have chosen this guy as the semi-dominator of W, not this guy. So this is a contradiction. This means that this cannot happen. So the semi-dominator of W has to be an ancestor of W. Was that clear? Sorry for the confusion. Okay, now I have to start writing bigger. I'm a bit worried because I wanted to keep all the lemmas on the blackboard because I'm going to need them later. We'll see what happens. Okay. I wonder if this is enough. This 4 right here. Okay, so what this means is that the immediate dominator of the vertex W is an ancestor of the semi-dominator of W. And this is easy to see, actually. Well, by lemmas 2 and 3, we know that these two guys are both ancestors of W, right? So in the path from the source vertex to W, these two guys must show up, and so forth. So suppose this does not happen. Then we must have that the semi-dominator is a proper ancestor of the immediate dominator. Right? This means that I dom comes first. We should start fast and go downwards to W. If this doesn't happen, then the opposite must be true. Okay? So we first reach the semi-dominator, then we reach the immediate dominator, and we finally reach this. Okay? Now why this cannot happen? Because, well, this guy is semi-dominator of W, right? So by the definition of semi-dominator, guess what? There's a path from this guy to this guy that only goes through vertices that has preorder greater than preorder of W. But all these guys in between S dom of W and W has preorder less than that, because they are in the path from the source to W in the DFS tree. So what we got here is a path S dom W, which avoids I dom W. This is a contradiction because I dom W dominates W. So this must move. We're getting there. Or not, it might be like. This is the last one. Then will be two more periods. There will be three more. I don't know. I lost count. Okay. Let's be W versus B. That means ancestor W. Okay, so consider any pair of vertices such that one's an ancestor of the other in DFS. Root B and W. And what this lemma is saying is that either V comes before the immediate dominator of W, or the immediate dominator of B has to come before the immediate dominator of W. Is that right? That was cool. Okay, so what this is saying is that this cannot happen. As the W. So the path from S to W must not reach this versus in this specific order. Why is this the case? So why this cannot happen? Notice that the item of W cannot dominate V, right? Because it doesn't dominate the immediate dominator of V. There's a path from S to V that does not go through the immediate dominator of V. So this guy cannot dominate V. This means that there's a path from S to V that avoids the immediate dominator of the V. Right? Can cheat and do something like this. And now if you just continue this path from V to W, you will get a path that goes from S to W, that avoids the immediate dominator of the second prediction. So this cannot happen, and as a consequence, either this or this must be true.
Marcus,
Yes.
it's time for the coffee break.
Yes, this is the last lemma that I'm going to prove, so I think this is a good time to have a break.
É melhor chamar presentes. Se eles não ficarem tristes com isso, mano, não tem quem que é?
I don't know how to put this on.
Assim, porque esse cara não tem como ter um domínio do cara que domina.
Testing.
Ele vem depois de fonte.
Tirou outra parte?
Tá, então.
Infelizmente.
Não, mas não é isso só que assim. Tem outra coisa lá. Tipo, esse cara não acho aqui.
Yeah, so now things start getting obscure.
Tinha mais coisa. Esse cara não pode ser dono dele.
Alright, I said that this would be the last method I was going to prove today. That was a fact. I'm going now to prove 3 theorems. Everybody loves theorems. This is this one. I think this is theorem 3. I think my note was wrong. I hope my note is wrong. Okay, so what is this theorem telling us? Consider the path from S to W. So, we know that the S dom of W is an ancestor of the path from the root to W. Right? This is lemma 3. So eventually, on the tree path from S to W, we'll come across this guy. And considering U. So the theorem is saying that for each U that lies on this segment of the tree path, if every single U satisfies this, which is the preorder of this S dom of U is greater than the preorder of the S dom of W, which means the the S dom of U is like either here or above. If this holds, actually it lies here or below, sorry. If this holds, then the S dom of W is equal to the I dom of W. Okay. Cool. How do we prove this? semi-dominator of W lies over here. Right? It could be W, but it lies either it is at the S dom or it lies above S dom because of lemma 4. Right? So if I want to prove that these two guys are the same, what I can do is prove that the semi-dominator of W dominates W. Right? Because if this is the case and these two guys are different, then I would have found a dominator of W that does not dominate the I dom. Right? Because this path from S to I dom does not contain the S dom. So if I prove that this guy is dominates this guy, then it must be the case that these two guys are the same. Okay? This is what I'm going to prove. All right. So consider any path from S to W as some kind of path. Okay, any path in G, and let X be the last vertex on this path, such that preorder of X strictly less than preorder. Yep. Okay. It might be the case that such X does not exist, but this would mean that every single vertex from S to W have a preorder greater than or equal to the preorder of W, including S. So that would mean that the preorder of the S dom of W must be 0, which means S dom of W is S. But S dominates everybody. So we would have that the S dom of W, which is S dominates W, which is what we want. So that's what happens if such X doesn't exist. If it does exist, then let's call Y a vertex that follows X on the path on this path P and has the following property. First vertex X such that vertex, so Y is the first vertex after X on the path that is a ancestor of W and is descendant of the semi-dominator of W. And this Y must exist because W is one such vertex. Okay, but I'm getting the first one, following X. Okay. Now the trick here is to look at this segment of the path. And I claim that for every vertex here on this path, we have that the preorder of this vertex has to be greater than preorder of Y. And why is this the case? Well, suppose this doesn't happen. Then there must exist some vertex. What do they call it? Z, not Z. VI, don't worry, Z. And what is some vertex Z such that the preorder of Z is less than or equal to the preorder of Y? Okay? But by lemma number 1, we know that there is a path from Z to Y that, every path from Z to Y has to pass through the common ancestor of Z and Y in the DFS tree. Right? So there must be some guy here, A, that is a common ancestor of both Z and y. But what do we know about A? Since A is an ancestor of y, we know that we know this, but also we know that A comes after x on the path, right? And x was the last vertex, such that was the last vertex on the path that had the pre-ordered index if less than the pre-order of the semi-dominator of W. So every other vertex from here on has to have a pre-order index that is greater than the pre-order of W. Okay. Pre-order. Okay. All right. But y is an ancestor of W, which means A is also an ancestor of W. Right, so A lies on the path from S to W in the DFS tree. And A has a preorder that is greater than the preorder of the semi-dominator of W. Wait, I think we already reached a contradiction.
Yeah.
Yes. We know that A is an ancestor of W and has a preorder greater than the S num of W. So A actually satisfies this, right? This means that A must be S num of W must be an ancestor of A, right, since they lie on the same path from S to W. So A satisfies this, and A comes before Y. This contradicts the choice of Y because I chose Y to be the first vertex on this path that satisfies this condition. Okay. So such vertex Z must not exist. So every vertex between X and Y has to satisfy this one. Has to have a preorder index greater than the preorder of Y. Okay. This guy does not exist. What does this remind you of? Semi-dominators, right? Come on. Every path from X to Y has, as an intermediate vertex, someone who has a preorder that is greater than the preorder of Y. Okay? So it doesn't mean that X is the semi-dominator of Y, but X is a candidate for a semi-dominator, right? Which means that the preorder of the semi-dominator of Y must be less than or equal to the preorder of X, which in turn is less than the preorder of what S num of W. All right. Okay. What do we do now? Yes. Ooh, okay. Okay. So what we get from this is that the preorder of the semi-dominator of Y is strictly less than the preorder of the semi-dominator of W, right? And we know that Y satisfies this condition. But if we look at the hypothesis of the theorem, we know that every vertex that satisfies the condition, except for the difference, must have the preorder of its semi-dominator greater than the preorder of the semi-dominator of W. So Y almost satisfies this, right? The only difference is that here we have a dot and here we have a plus. So the only way to satisfy these two things at the same time is if Y is actually semi-dominator of W, right? Otherwise, if Y would be a proper descent of W, then Y will satisfy this condition, but it would not satisfy this one. Okay? So what we get from these two is that Y is actually semi-dominator W is the only possible case. Right? So say stop. But this means that the semi-dominator of W appears on the path from S to W. Right? But I chose P arbitrarily. I did not impose any condition on the path P that I chose. This means that the semi-dominator of W has to appear on every single path from S to W, which means the semi-dominator of W dominates W. This concludes the proof, because from this we conclude that the I dom of W must be equal to the S dom of W. Cool. Just a couple theorems more. Theorems 4 is kind of similar. All right. What is this telling us? So, if you consider every vertex on the tree path from the S dom of W all the way to W, and take the vertex for which the semi-dominator of U has the lowest pre-order index than any other vertex in this path, then it must be the case that, first, the pre-order of the semi-dominator of this guy has to be less or equal to the pre-order of this guy, and the immediate dominator of U has to be equal to the immediate dominator of W. Okay. I'm going to put this first because it's trivial. Well,
Marcus?
Yes.
Could you show again what this actually means then? What is W?
have this guy, and have W. And this is the tree path in the DFS tree from S dom of W to W. Okay. Now, what this is trying to say is that for all vertices in this path, from here below, take the one which has the lowest take the one whose semi-denominator is higher up in the tree. Okay. So if you take this guy, then the semi-denominator of this guy is actually either higher or is equal to the semi-denominator of W, which is this guy, and the immediate denominator of this guy is equal to the immediate denominator of this guy. So this actually gives us a way to calculate immediate denominator based on semi-denominators. Both theorem number 4 and theorem number 3 would be crucial on building the algorithm to find the immediate denominators fast. Okay. This inequality is easy. Look at the immediate child of this guy, call it D, on the path from this guy to the. Well, this guy satisfies this condition, right? It's between the semi-denominator and the vertex itself. But since the parent of this guy is the semi-denominator of W, and the parent of vertex is always a candidate for a semi-denominator, you know that the pre-order index of the semi-denominator Z must be less than or equal to the pre-order of the right? Because this guy is a candidate for semi-denominator of this guy. Yeah, but U is chosen so that this value is minimal, right? So we actually have this. And yeah, here we go. Fairly easy. Okay, that one's the hard part. Well, actually, the demonstration of this theorem is quite similar to the proof of theorem number 3. So we'll take any path from S to W and find X and Y, satisfy some properties, and then we will end up figuring out that item of U actually dominates W, which would imply that they are the same. Let me formalize this. This guy dominates UY. That's stupid, of course. Okay, so lemma 4 guarantees us this. And since U has to satisfy this property in particular, U is a proper descendant of the semi-denominator of W. So this must hold. Using lemma 5. This cannot happen, then that has to be true. Okay. Okay, now I'm going to use lemma 5. And I know that U is an ancestor of W, right? So by lemma 4, I mean 5, either U is an ancestor of item W, or the item of W is an ancestor of item of U. Okay, but this is not the case because we know that the item of W is a proper ancestor of U. Right? So this doesn't hold, so this does hold. Okay. Yeah, okay. So once again, I want to prove that these two guys are the same. Right? So I'm going to use the same idea that I use on theorem 3 to prove that these two guys are the same. I'm going to prove that item U dominates W. And by the same argument that I use here, this will imply that these two guys must be the same. Okay. Otherwise, item W, item U, W. If item U dominates W, then it must also dominate the immediate dominator of W, right? Because this guy is the immediate dominator, so every other dominator of W must dominate this guy, right? But clearly, if this is the configuration of the tree path, then item U doesn't dominate item W. So if this guy dominates W, then these two guys must be the same. Okay. All right. So once again, let's consider any path from S to W. Once again, let X be a vertex with the following property. First vertex such that the order that's skip the last the order by down. Once again, if such X does not exist, this would mean that everyone here has preorder greater than or equal to the preorder of U. But this guy is 0, so this guy has to be equal to the item of U. But as dominates W, then we would be done. So otherwise, such X exists. And then I'm gonna take another Y, satisfy. What exactly does mean satisfy? Yeah, same stuff. First vertex. X should be the last vertex. First vertex. After X. Such that I got U, an ancestor of Y, ancestor of W. Once again, W is one candidate for Y, so such Y is this. Okay. Where am I? Okay. So, same story. Every vertex of this segment has to have a preorder index that is greater than preorder of Y. The preorder of everyone here is greater than preorder of Y. This will imply that X is a candidate for some identifier of Y. So, preorder S down Y must be less than or equal to preorder of X. Yes. What else? Here we have. Okay, it's gotta be ugly. Well, X is the last vertex to satisfy this, right? So this holds. And by lemma 4, we know that the item of W is the ancestor of, is one ancestor of the atom of W. So this also needs to hold. Okay. Right.
Why does it less than equality holds?
Because we know that the item of W is an ancestor of the item of W. So in the DFS tree, you will reach the item first. So the period has to be less than or equal to the period of item of W. What is E? Sorry. Today's not my lucky day. I want to reach a condition on y with respect to u. I want that the pre-order of the atom of y has to be less than the pre-order of the atom of u. Where do I have this? Do I have this?
Yes. The chain of inequalities.
This is u, right?
Yes.
Oh, that's so stupid. Okay, cool. Thanks. So we know that this holds, right? And once again, y almost satisfy the condition. Does it? Okay, I have to prove two things first. Okay. First thing to notice is that we cannot have I asked W to be a proper ancestor of Y, which is in turn an ancestor of W. But if this would hold, then Y would satisfy this condition, and then U would be Y instead, and not U, because the preorder of the atom of Y is less than the preorder of the atom of U. This will contradict the choice of U, because U is chosen to be the minimum that satisfies this condition. So this cannot be true. So our option is, so we know that this must be true. The item of U, an ancestor of Y, which is an ancestor of that amount. Which is in turn an ancestor of. Okay, now what I'm going to prove is that we cannot have this. Y cannot be a proper descendant of I down of W. Or U. The U. Okay. If this were to happen, then we will, the tree path from S to W will look something like this. S, and then we will have I of U. I should have made a drawing of this. done. Okay, but I know that pretty easy that S dom of y has to come before S dom of u. So let's do something like this. Please correct me if I write something wrong. This holds that must be true. Is it enough? S dom y. Wait, what? Oh, I'm stupid. Okay. I got it. So we know that the pre-order of the S dom of y is also less than the pre-order of I dom u. Right? So it must come first on the path from S to W. So actually I made a mistake here. So S dom of W must come first. And then I dom u. And then S dom u, where does y get? Where does y come in? It doesn't really matter. This holds the. Okay. This was the description of the tree path from S to W, right? First, we must have S dom y before I dom u because of this equality. Then I dom u must come before y because of this that I'm assuming is true. And then y is a ancestor of w because of choice. I chose the y to satisfy this. Okay. Contradiction time. By the definition of some I-dominator, I know there's a path from this guy to this guy that only uses vertices with high pre-order indices. In particular, every guy on this path has pre-order greater than the pre-order of y. But every vertex on this path has pre-order less than y, because they come first in the search. So this path avoids I dom u. So if you make a path from S to S dom y to y, avoiding u, then falling to w, you found a path u. You found a path from S to u that would avoid I dom u. This is a contradiction. Okay. I did not cheat here, right? Because y is not necessary yet. Okay. Theory is not over. I just proved that this cannot happen. This is what I assume true, and then we get contradiction. So this is not true. So what we get here is that y is an ancestor of I dom u. But I dom u is an ancestor of y by choice. So the only way these two things can happen at the same time is if I dom u is equal to y. Okay. So once again, we just proved that the I dom u appears in every path from S to W because P was taken arbitrarily. So I dom u must dominate W. And if I dom u dominates W, then these two guys must be the same. Otherwise, because this guy does not dominate this one. Yeah, that concludes the proof. Yep. Sorry for the confusion. Is everything clear? Do you want me to clarify a bit more? Yes.
Could those definitions and the theorems apply to what kinds of graphs?
Any kind of directed graph. Yeah, as I said in the beginning of the class, I am assuming that S reaches, the source vertex reaches every other vertex. You can just pre-process this beforehand and remove every vertex that is not reachable from X. Because the theory of dominator doesn't make much sense if there is no path from source vertex to some vertex to the graph. So you can just disregard it. All right. Okay. Before I prove the last theorem, let me just show corollary first. I only ran out of time. Okay, this is already new. I'm just gonna show this corollary. The proof of it is like immediate from these two theorems, and then I can continue maybe tomorrow with the last theorem and how to implement all this stuff. Okay. Corollary. All right, there's the corollary. So the statement is pretty much similar to the statement of theorem number 4. Actually, this condition is exactly the same. So despite the theorem is stated like this equality always holds because of theorem number 4, we just proved. But this part is useful when, for instance, this is W and this is U.
Okay.
W and U might be the same vertex, right? It might be the case that this guy is minimal when W equals U, in which case this theorem tells you nothing about. So, if this happens, then this equality is satisfied, and then by theorem number 3, we know that this holds, right? Because U is chosen to be the vertex with minimum pre-order of the semi-dominator, right? If yeah, and we proved somewhere around theorem number 4 that the pre of this guy is at most the pre-order of its parent, right? Which is not one. Oh, this is tricky. Where is stuff? Somewhere around theorem number 4, if you satisfy this condition, this minimality condition, then the S-dom of U is actually less than or equal to the S-dom of W. Right? We proved it somewhere. So, but this is for any U. So if we know that the preorder of S-dom of U is less than or equal to the preorder of S-dom of W, and also greater than or equal to W, then it must be the same. So this first case is when basically this case is useful when U equals W, and then all those stuff happen. Okay, that's pretty much it. This will be like the core of the algorithm to calculate semi-dominators and immediate dominators. Okay, so basically the whole the steps of the algorithm will be basically first calculate the semi-dominators using theorem numbers 3 and 4, and then once we have the semi-dominators, we can calculate the immediate dominators using this corollary. Okay, that's pretty much how it works. Any questions? Let's eat food.